Good evening, y'all. Welcome back to another Sunday night of nerdery. It's good to see all of you here again. Hey, some familiar faces out there in the chat. Chris, Dave, Nate, good to see you. Nate, I hope you're doing well out there. Brokeboth, hello as always. Pleasure. Yeah, it's gonna be a fun week, y'all. We got a lot. My wife earlier today, Mary, who says hello to all you good people, Mary said, she was like, you had a lot of packages this week. And it's true, not all of them for this project. I also reinvested in, in some lighting, or some ham radio equipment for the coming summer. Oh, Thomas is just poking in and then is lighting a show very soon. Thomas, have a great week. You can catch up on it later. We'll give you all the updates. You can come back and watch the VOD and laugh about how all the stepper things I'm doing are wrong. But you can tell me about it next week. Good luck, break a leg. Yeah, lots of stuff. Where do we start? Let me tell you what I think we're gonna do this week, which is always 100% accurate and never over ambitious. And then I will flash back because last week's was like a little 15-minute snippet because we were coming back from a vaccine road trip. So 2 weeks worth of updates to give you, and then we'll plug into the thing that we're actually gonna do this week. Yeah, seem like a plan? So things I think we're going to do this week include stepper motor playtime. I got a pack of NEMA 17 stepper motors in the mail, and we're going to wire them up to an Arduino because, of course, the Demilight control boards, right, the heart of this system are ultimately an ATmega 32.8 controller, right? It's essentially an Arduino on a smaller board, right? So we're just going to use our old friend, the Arduino Uno, or maybe the Mega, and play around with some stepper motor controls. So we've got some stepper motors, we have some stepper motor drivers and some convenient little breakout boards for them that we'll play with. And I'm hoping to get to the point where we can learn whether the existing stepper control libraries are going to play nicely with DMX reception. This is the issue that I'm afraid that we're going to run into and we'll have to solve is the same issue we were having with the truss warmers, the NeoPixel truss warmers on the micro stage. And speaking of the micro stage, you'll notice the view is slightly different and slightly less crappy, although a little bit overexposed. And that's because I've changed cameras over there. It's my iPhone being a tethered camera. So the quality is much better, although the control over the parameters is actually worse. So, but thankfully we won't be over here too much tonight. So I've not dialed this in quite yet. But you'll recall when we were working on the truss warmers here, we saw an occasional flicker in the NeoPixels. And though I'm still not 100% sure, I think that had to do with the fact that the timing requirements of the NeoPixels were pretty specific. And the DMX reception, when a new DMX frame was received, it would sort of butt in and interrupt that very critical timing. Stepper timing, right? Stepper timing is not really so much a thing. In as much as the control into these driver boards essentially is every time you pulse a single connection, it will move one step, or one half step, or 1/4 step, or 1/8 of a step, or whatever unit you set it to. So timing is not super critical. I'm curious to see if we start shooting DMX into these things, are we going to end up in a situation where we're seeing stuttering because the controller is pausing to process its DMX input? Not quite sure. So we have lots of playtime to get to before we run into that issue at Crash and Burn, but I think that'll be a lot of fun. So that's the project for tonight, is starting on integrating steppers with what I realize I've been calling a motorized winch since the beginning of this project, like 4 weeks ago. But tonight there will actually be motors on it, so won't that be nice? But before we get there, let me move the steppers and the Arduinos and stuff out of the way for just a second. And tell y'all about what I've been up to with these winches and why there's a build plate just sitting on the desk here for the past couple weeks since we've seen each other. So y'all will recall the last time we were actually doing streamy things together, this is what the miniature winch looked like, which is the same mechanism that we've explored at this point. It's got a ratchet and pawl. It's got a couple of friction washers to drive the I don't know what you would call this, the handle wheel tight when it is screwed on, and then loosens it when it is screwed off. Right? This is the mechanism we've been playing with. Let me get this working threading properly, because it will be important to understand how this one works before we dive into the other one, because it's somewhat more, the new design is somewhat more compact. So, right, when we have a load applied and this threads in successfully, maybe I think I'm just binding on this shaft at this point, which is going to be unfortunate, because that's going to mask the actual, yeah, there we go. So when we wind in a what we'll call a load-in direction, a tightening direction. Let me zoom out just a little bit here. When I load in, you can see the ratchet starts to turn. You can probably hear it clicking there, right? You can see the thread pulling out of my fingers and onto the reel. And then as long as there is a load applied to the line, when I start unwinding, the handle wheel here, which is threaded onto this shaft, starts to unscrew a little bit. That reduces the friction between the handle wheel and the shaft, and more particularly the ratchet and the shaft. So we reduce that friction to the point that the barrel actually starts to slip against the ratchet, right? So it slips a little bit, but that also tightens it back against the handle wheel, right? Which tightens it up, increases friction, and prevents it from moving. So as we rotate counterclockwise, we can loosen, but if we let go, right, there's enough friction to keep the system in place. And as we move back clockwise, we tighten, lefty loosen. Yeah, so that's our key ratcheting mechanism here, and this is our functional prototype, right? This is our demo that we use to sort of work out how that mechanism works, and I'm actually really delighted how well it's turned out. You know, the biggest thing we had to implement was there was so much friction in the very first design because it was just PLA on PLA, and now the design has these skateboard bearings in it, these cheap 608 bearings that allow us to have less friction when we're really side loading this thing, right? So this is where we left ourselves a few weeks ago. This is more or less where the design is now. So this works fine. The problem is its size, or the problem that I have with it is its size. So if this was going to be mounted, say, in the micro stage, right? It's not unreasonably big, but it's bigger than I would want it to be. So I was trying to figure out ways to shrink this design down as much as possible. And I had a demo of this prepped, and then you might be able to tell this is not actually what it's supposed to look like. The new barrel design sheared in half right at the edge of the thing there. So actually, I printed a fresh one with a couple of extra fillets to make it a little bit more robust. And I figure a good way to explain what the heck is going on here would actually be to assemble this new version. Which means, you know, I know, Nate, I know you've probably been missing some of the filing that we used to do, and some of like the part fitment, but don't worry. That's what we're gonna start with tonight is a filing stream. So we'll break some supports off and we'll get some things done. And we'll start fitting parts together. But the whole goal of this new design was to try and like minimize the amount of space that it took up, you know, to go from a frame that was almost 80 millimeters tall to one that I think is like 36 millimeters tall, just for aesthetics and compactness and, you know, all the other reasons we try and make these things small in the extent of the Demilight project. We'll just break some supports off there. I did a couple of iterations of like the tolerancing in these channels here, and we'll see why that's important in a second. That's going to be a friction interface where two parts have to slide past each other. And when I first designed it, I was like, oh, you know, maybe like 0.2 millimeters would be fine, forgetting that I was going to put a bunch of supports in there to print this funky shape. And just the amount of filing that required was untenable. So this, I think, will be somewhat more pleasant to watch being assembled. And to assemble, frankly, if I'm being entirely selfish. We'll just break off a few supports there. There's a couple more in this side. Ooh, nice. Nate has his Prusa up and running. That's fun. Yeah, I got that. It's true. The post-processing is a part of any print, but oh, Cookie's at this point. Cookie's accepting so Cookie, actually, this I know you've been working on lifting devices as well. Are you working toward like a chain motor design with actual? I guess you say it's not going to be that small. I wonder like how miniature it's ultimately going to be. But are you shooting for actual like chain links? Because that's a super interesting part of that mechanism that you may have noticed I've decided I'm just not going to handle, right? I'm probably going to use like line of some kind or twine or rope, just because that's going to make things I think a little bit easier. Ah, fishing line. Yes, very good. Yeah, I looked a little bit, you know, because you look at like the cutaway videos on YouTube of like how chain motors work and like what that wheel mechanism is that actually grabs the links of the chain, and it's super cool, but kind of daunting to do in miniature, right? Okay, so that is the new frame piece fully cleared, and you can probably guess that we're going to put another, we're going to put one of our bearings just in here, but I'm actually going to save that until a little bit later. This is the new barrel, right? That new centerpiece there. Are these PLA? Yeah, these are all PLA parts. I did a few of the early test prints in PETG. I want to say this one's PETG, but everything else is PLA. I think probably finally, when we nail the design down, this part, the barrel, which needs to be fairly strong, will probably be PETG. But it doesn't make a huge difference, I don't think. I printed these in what I would call like lazy draft settings. So like when I was doing some of the load testing, this is printed with like 5 perimeters and 10 top and bottom layers and 40% infill. And this I think I did my usual like 2 walls, 15% infill. Like it's not necessarily going to be as strong as the final part. So we'll see how that goes. So we got those. We got our barrel. Let's grab these parts from the other version. So these are a pretty critical part of the new mechanism. These are the ratchet part of the new winch. So let me put these parts in here next to the old winch and kind of give you a sense of what we've swapped out, right? So the barrel itself is relatively the same, right? It's got a small shaft section. This is where the line would be attached. Although ultimately what I think I've settled on, and I think I referenced this in the 15-minute teaser last time, is rather than trying to make this actual winch mechanism a winding point, this will ultimately have a coupler on it to a shaft, much like the Kabuki drop did, something kind of like the equivalent of the Thomas coupler. And we'll have multiple winding points, multiple pulleys or wheels, I guess they will be, along there. So the point of this will just be control the like rotation of that shaft, but this barrel section really won't be a winding point itself. That section here, maybe I should put the bearing in here and we can start to assemble this, and that'll make some more sense. So let me pull out one of these pretty greasy 608 bearings here, and I imagine this will need a little bit more filing. One of my earliest ones still here. Yeah, so the early one, my fit one was way too tight, and you can tell I had to super glue it back together for testing. So I've loosened the tolerance a little bit since then, but I really want this part in particular to be a snug fit, so this bearing doesn't stand any chance of running away. And because of how it prints, there's often a little flat section up here at the very top. So I'm just going to file that out real quick. That's something I found in the testing. So we will, yeah, there we go. We'll just press that bearing in there. So that's our skateboard bearing. That'll be sort of the load bearing point of this frame. And we'll push the barrel through that. That's also a pretty snug fit. Ooh, it's a very snug fit. Try not to break the barrel. There we go. It's a little bit too far. We'll just even that back up a little. All right, there we go. So that's our barrel sitting through our bearing there. And of course that rotates freely because it's in that bearing surface. Let's see here. Gonna get that bearings popping out on me just a little bit there. There we go. And then just to hold that in place, what we've been using is a couple of these like retaining pins that are sized for 1/4-inch shafts. And I know I have a bunch of them around, but because I'm lazy and in a hurry, I'm just going to steal them from this other design. And all those are there to do is just like, if this were to experience a lot of side loading, the shaft couldn't actually slip out of the bearing. So we'll put one on a clip in the inside, and then we'll use one of these other shaped ones. I'm sure these two things have different names in actuality, like a retaining. I think you found the name of that other one, the sort of U-shaped retaining clip last time. Maybe it's just a retaining clip. So those just sit in 2 little grooves there, and they're a little bit they stand off just, you can probably tell they stand off just a little bit from that surface. They're not rubbing on the bearing. They're just so that, like, if something were to happen and this were to start to apply some load to the side, we're not going to, like, lose this bearing coming out. And like I say, in the final version, the shaft that would actually support the lifting wheels would be attached here. Haven't developed that yet. All in good time, right? So, yes, so now this is the tricky part. Is the ratchet. So make sure my ratchet wheel is going the correct way. So we'll need to put one of our friction gaskets here. Let me think about which of these was the appropriate diameter. I actually might just steal this one as well from the previous winch. So that's just a little piece of rubber there to increase the friction between those two. We'll put our ratchet on there. It's a little bit snug, so lucky ducks, you get a little bit more filing out of this evening. Because, of course, this ratchet wheel isn't fixed to any of the shafts, right? The whole point is that it runs free on that barrel arbor. I realize I've been saying barrel as if it's a term for that shaft piece, and I think what I mean is a barrel arbor, which is a term from clockmaking that I am both stealing and don't 100% understand the meaning of. But since this is a project that is sort of made up from whole cloth anyway, I feel okay about making up my own terminology, as it were. I think I mentioned last time one of my favorite, really like deep dive nerdy channels here on the YouTube is ClickSpring, who makes incredible clocks, and is currently in the process of like developing a recreation of the Antikythera mechanism, right? The ancient Greek or Mediterranean astronomical time-telling device, which is kind of an incredible piece of history, and no one is quite sure how it was made. And so a part of the delay, I think, that they're experiencing is that they are discovering through the recreation of it himself and some like other horologists, the term for clockmakers and time tellers, are discovering that there are things that the process of remaking one of these with ancient methods is telling them about how it must have been constructed and what it might have been for, and they're actually like publishing scientific papers about the purpose and the history of it based on what they now know because of their work, which is super cool. Let me make sure I get this right. So this is going to ratchet this way. Yes, okay. So, and then make sure that can spin freely. It's a little bit of a tight fit, but that'll be okay. So here's the new stuff. Here's how this ratchet goes in. We'll see if we can get this on camera. So this ratcheting mechanism is actually two separate pieces. They're identical, deliberately. And they have some teeth which provide some options for where one end of a pair of springs is mounted, some little tiny springy boys, and the other end hooks onto these little tiny hooks on the opposite piece. And the two pieces, if they fit together, rotated at 180 degrees. So they're a little bit of a bear to get aligned, and it'll be even more so when we have to do this sort of in place in the device. But when we attach a spring, here, why don't I just do this? We'll attach a spring between one of these clips and one of these ridges, if you will. Let's see if I can get this to clip on. This is one of the flaws in this design, is like there's actually not a clearance that we would need. But you can see how these two halves are drawn together by that spring force pulling against those two things. And the multiple ridges here are just so we have, depending on what the spring is, we have multiple options for where to clip this end of it. Then we do a second one down here, so we have a symmetrical sort of springing force. And attached to the back side, or the other side of these two pieces, are the ratchet pawl. So that's actually what's going to be engaging our ratchet wheel. So as the ratchet wheel turns, it will be pressing outward on these teeth, so which will press outward, but because the spring is pulling them in, they'll be pressed outward and then snap back in. Press outward and snap back in. And they are not free to rotate because they are held in place by these notches in the frame. So let's see if hopefully this will all work. This is not the primary focus of what we're doing tonight. So if it doesn't work perfectly, that actually will be okay. This is still very much a beta design. So one of the pieces sort of slips in like that above the barrel shaft. The other fits in under here. And this is where I say it gets finicky, because we kind of have to get both of these pegs and holes aligned at the same time while also working sort of inside of the mechanism. Chris, good question. Chris asked, do having two of the pawls give you more resolution? It's a good question. So the current ratcheting, the current ratchet wheel has, I think, 16 or 18 teeth, has an even number of teeth, so it's symmetric in a way left to right. And so currently, no, because the pawls, the jaws of the pawl are symmetric. If everything was aligned correctly, which it seems like it's not. Gosh, this came together nicely. Let's see, is this true? Let me actually count, because I did experiment with a 17-tooth wheel, and I don't think this is one, but this is engaged here, so we'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17? No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, this is my 17-toother. Okay. So, in theory, yeah, so in this, I hadn't intended to print another 17-toother, but we'll see how this goes. You can see the tooth on the right, on the screen left here is engaged, and the one on screen right is not. The idea is if this rotates half a tooth worth of rotation, the right-hand pawl slips into place, and the left-hand pawl doesn't. And the pawls sort of alternate which one is grabbing a tooth at any given time. That's the theory. In my earlier testing, it seemed like that the back and forth motion of this pawl arbor was causing those teeth to not always like bite down and latch into those points like they should be. So I was thinking of going back to a 16 or an 18 tooth wheel, but since I seem to have printed another 17 tooth wheel, maybe we'll give it another go. I also, gosh, this hole in the bottom of the frame to get this other spring in, you'd think would be a really obvious thing to add to your design where you're putting a thing in, but no, that's new to this version. Everything else had a solid bottom, and I was like tweezering in to try and get the spring inside the frame, which is very silly. So this is already a much more pleasant process. Oop. So we'll kind of go in through there with a spring. Time to preheat the printer. So I think we're going to do a test assembly of this so we can show it off, and then we're going to focus on, well, I say focus on, you know how good I am at focusing on, but tonight is about stepper motors. I have new stepper motor toys to play with, but I wanted to get this assembled and share it with y'all so that we have a sense of like what these stepper motors are actually going to be driving once we get them working. Let's get that. Now that I sort of have a go-to size of spring, not that I could tell you what it is off the top of my head, I am thinking I'm going to redesign this so that it only has one sort of catch tooth here, because, and you'll see this when I put the top spring on, the alternate attachment points are nice, but they do get in the way of the motion of like the direction of travel of the spring in a kind of annoying way, in a way that causes the spring to often slip off. Yeah, you can see we've dislodged this bottom one here. Maybe I'll go to one further point and see if that helps it to stay. Safety glasses? The worst that happens is like a piece of metal spring flies into my eye here. Yeah, Chris, listen, no one here is expecting me to stay perfect. I hope no one's expecting me to stay perfectly on topic this entire time, or, do anything like what I said I would do. But if you are, you can believe whatever you want to believe. It's a free world. All right. Whoa. Well, that spring's gone forever. Yeah, I need to do a revision of what these hook shapes actually look like. Oh gosh, it's all falling apart. Well, I'll tell you what, let me get the top spring on so I can demonstrate the mechanism for you, and then we'll do a revamp on these. That won't be too painful. That's a pretty straightforward print. So that's that ratchet, and we'll get this top spring on here. There's that. And there's... yeah, I don't have any, as Dave points out, I don't have any spring-related stories, which is probably going to save us from like 2.5 hours of spring talk. Do I have any spring-related stories? I mean, this would, while I'm fiddling with something, that would be the time. Gosh, I don't recall any. Thinking back to like the automations projects we've done, but so few of them involve springs that you actually want to deal with, you know? Like there's springs inside of the motor clutches, but the whole point of those is to stay far, far away from them. You know what? I'm gonna, you know, I'll do to help this out. I'm just gonna go. I've been going to the 4th peg, and I'm gonna go to the 5th here at the end, just to give myself a little bit more tension on this spring, which I think will help it stay in place better. I've kind of mangled that one now, but that's all right, because as we already know we're gonna reprint these, so. Okay, there we go. So that's holding in place. So it's going to be a little bit asymmetric, right? Because I'm only going to bother to put the top spring on because it's going, well, you see how it's going? But that is the mechanism now. And so in theory, as this rotates, in theory, I also might have just too much spring force now. Oof, that's a lot. That's a lot of force. Yeah, I guess what I've given up, so in this design, right, the ratchet wheel, which is here, right, has some mechanical advantage against the spring, against the pawl, because it's a class 3 lever, right? Like the spring is acting on this short of a moment arm, and the pawl is this long, so that the ratchet wheel has some mechanical advantage. Here, there's no mechanic. It's sort of it's pulling linearly against the ratchet wheel. So this one, even though it's not an identical spring, but just from force of feel, it's comparable. But this ratchet wheel is a lot harder to turn. But I am getting that, you know, just turning this by hand, and maybe I can even put our friction wheel on it and try it. Let's see. Maybe I'll just do, where's my hand wheel? Yeah, we'll just do if this will clear, we'll just do the hand wheel for now. There we go. So now, oh yeah, it's significantly harder to turn, but it's very, very satisfying and very affirmative. And I'm trying to tell, let's see if we can look down in there. I'll really zoom you in. If we're getting that half step action. And I think we are. So right now we're latched. It's really hard to see. I should do this in clear PLA next time. But I'm lashed on the right-hand tooth there, the screen right tooth, and the left tooth is not latched. You can sort of see that tooth is sitting just sort of in the middle of a gear there. And then if I do one click, now I'm latched on the left side, but I'm also latched on the right side. So part of what's happening here is this shaft, because it's really only held by this one bearing, is actually flexing up and down because both teeth really want to be mated, right? So you can even see as I put torque on it, it's tending to push the shaft up or down so that two teeth that are not directly opposite each other can both be engaged at the same time. So if I put some more rigidity into this shaft, I might be able to make this sort of, you know, half-stepping of the ratcheting pawls work. I don't know that that's necessarily something I want to devote the energy to. Although, look, you know, even there, you can see we're engaged on the left and not on the right. And if I click one click, we're engaged on the right and not on the left. But partly this is helped by, like, I'm doing this with my fingers, and I can sort of feel and see what's happening. But yeah, it's really, there's not enough stability in the shaft to really make that work. But I think good progress here and things to be considered. And ultimately, I like this design. I may end up going back to just a single pawl, and maybe coming in from with some additional support out here to keep this shaft a little bit more aligned or something. But in terms of minimizing the overall footprint of the frame, I'm quite pleased with this design, both from a sort of an XY perspective, right? The height of it is less and the depth of it is about the same, but also in terms of front to back, right? One thing I was really trying to eliminate was the fact that this pawl had to really hang way out in front of the frame mechanism, and this has kind of condensed things down a little bit tighter. Also just looks cool, which I don't mind. So that's the winch developments for the past 2 weeks, really, is the development of that mechanism and the printing of it. And clearly some ways to go, like adjusting those teeth, adjusting the sort of like what's holding the shaft plumb. Do we want to do 2 pawls or 1? But I think the basic theory is sound. So yeah, so that's been a lot of fun. So there's that. I think I showed in the pre-show, but I have not mentioned yet, tonight's beverage of choice, I always remember is a double daisy cutter from Half Acre Brewery here in Chicago. It's very tasty. Those of you who've ever had daisy cutter, it tastes like fresh mown grass in a really delicious way. This tastes like half as much grass and twice as much bitterness, which I don't mind. Very delicious. If you're drinking something interesting, I always want to know, even if that's just, even and especially if that's just water, because drinking is not everybody's thing. No pressure, and hydration is good. Ah, yum. All right, so winch updates aside, let's move on to stepper motor stuff. We're only half an hour in. Dave, Chris, you detractors out there, like, oh, Jeff's never gonna get to the thing. See, we're getting to the thing only only half an hour in. Seems fine. It's pretty good by our standards, I think. So let us dive into this thing. Ooh, Cookie had some hot cocoa and gonna get some bubble tea. Ooh, nice. In Chicago, it was like 47 degrees today. It was a very chilly day, but I know in most of the many other places it is warming up, and that is wonderful. Oh no, Dave's drinking ice cream from a dead freezer. Oh, that's so sad. My wife got... Okay, first divergent story of the evening. It's fine. My wife and I are in a communal Dungeons and Dragons group that recently finished a very long and extensive campaign, and so we're doing a series of little one-off adventures in between. And so last night we played a game called Honey Heist, in which you all play a series of bears who are criminals trying to steal some honey without being detected. What made me think of it is that to celebrate, my wife got us a really delicious like sea salt caramel and honeycomb custard ice cream from a local place. Super good. Our freezer is also on the fritz, so it was kind of like somewhere between like custard and a smoothie. It was really good, but a little bit disappointing. So I feel my heart goes out to you, Dave, and drink some ice cream in for me as well. So what we have here are some smaller size NEMA 17 stepper motors, right? There are many different varieties and sizes of them, but this is sort of a small-ish size, which I'm guessing will provide enough power for us, and if it doesn't, will at least give us some good data. It's also not super duper heavy. We could have gone with something heavier, but this seemed kind of nice. They ship with these 4-wire extension cables, which is awfully handy. Then I've got it plugged in here to a little breakout board. And on this breakout board, we have, this is a DRV8825 driver board. That's actually, I've stuck a heatsink on top of it. This IC is is the part. That's the DRV8825. And this is a little convenient breakout board for it with some passive components and a potentiometer to set its maximum current. So they ship just as this. That's your stepper motor driver board. And then I also bought, for the sake of experimentation, some of these little handy breakout boards that have some useful connections on them that'll be useful for us tonight. So we're gonna need to get this all wired up for power, and then we'll play with getting the motor running. Chris has SparkFun board. It's certainly SparkFun style. This was a no-name Amazon one. Please use 9-volt 1 amp power. Yeah, we can go bigger. The thing we're gonna need to do before we, oops, that can stay there. Before we actually get into that though, is TRV 8825. Set the maximum current that we're going to apply to our stepper motor. So the driver board will handle up to, I think, 1.5 amps in theory with no heatsink, and up to about 2.5 amps with a heatsink. The stepper motor, though, is only meant to be driven with, I think, 1.5 amps. So we're going to need to just do a quick calibration on this driver board. And I'm just off camera here looking up my cheat sheet for how the voltage on the potentiometer relates to the maximum current. And I'm just rapidly scrolling through things which nobody needs to watch me flash through. Current limit is, the current limit in amps is twice the reference voltage. So for 1.5 amps of, 1.5 amps of current here, we're going to set the reference voltage on this board to be 0.75 amps. So let's unplug it from things, and let's take a second and get it wired into power. So let's zoom out a little bit here, and we will grab a couple bits of wire. So that will be our, I think we're going to run this off of 12 volts. You can actually run these steppers off of a fairly wide voltage range. Just going to give you a little tummy cam view as I grab a little bit more bell wire from the rack. Because it seems like the microstage is centering around 12 volts. I think we're gonna do our experiments at 12 volts and see how that works out. So there are our two power inputs there. We'll plug those into our leads, and we'll get the multimeter out. So here we can actually do a slightly better view here. So we'll get the meter. Let me zoom out even a little bit more so I'm not too worried about it. And we will turn our voltage up to 12 volts. I know this PCB says 9 volts, which makes me just a little bit nervous, but I'm sure it's fine. Turn the meter on, always helps. And we will find a convenient grounding point. Let's make ourselves our own convenient grounding point. There's these connectors over here are power in 2 grounding points and a 5-volt connection point. If you're tying it to, a 5-volt microcontroller. So I'm going to use that second ground connection here as the point of connection for my multimeter. So we'll just come in here to this, which I should be able to measure my reference voltage on. I don't know if I need to have it enabled to make this happen, because I'm not really, well, it helps if my ground is ground. My ground is grounded. Let's get that properly plugged into that header there. 28 millivolts. Let's see if adjusting that changes anything. Grab a little tiny Phillips head here. Not tiny enough Phillips head. Let's try a little tiny flathead and see if we can adjust this potentiometer here. Let's go all the way clockwise and see if anything has changed. 0 millivolts. We go all the way counterclockwise. No, nothing has changed. We're at 0 millivolts either way, which makes me think that maybe we need to make sure this is enabled. Let's see. Yes, that makes good sense to me. So to do that, I should have pulled the breadboard out earlier. Let me pull out a breadboard. Here, you can look at the beautiful table. Well, you can look at my beautiful face while we do. There is something about, like, being on stream with all you maniacs that like has definitely made me sorry, you're all wonderful people, but I'm definitely more carefree about like, you know, hey, is this the right voltage? Because if it's not and there's fire, y'all are happy. And if it is, if it works and it's fine, then I'm happy. So like somebody wins no matter what, really. So what I'm going to do, so what I'm thinking is, so there are 3 connections here, E, D, and S for enable, drive, and I think step. What is SLP? What's my SLP pin here? Oh, that's my sleep pin. So yeah, so right now the driver is disabled, which is no good. Now what I don't understand. Well, clearly some things I don't understand, but let me get, I'll just use the Arduino that we're going to use to control this thing in a little bit. And we'll use that as a source of 5-volt power. So we'll have to pull up a couple of pins here to actually enable the driver so we can set the current. So why don't we start doing some wiring setup here. We don't need to look at our computer just there yet. So let's bring, sorry, you're gonna a little top of head cam as I look at pins on here. We'll bring our 5 volts over to our breadboard. We'll bring our ground over to our breadboard. And then, so that's a pretty awful jumper wire there, we can do better. Let us use one of these guys. We'll bring our ground over to our breadboard. And we will need to make sure that we pull the, is it enable? Probably enable. So let's, enable I think has to pull high. So I need actually a different flavor of jumper here. So we'll pull enable high. And now let's see if we have, do I have spares in case we let the smoke out? I do, Chris. I have, I think 5 of these driver boards and 3 breakouts for them and 3 stepper motors. So we are well prepared. Oh, you know what it is? I need to make sure that these 2 things are sharing a common ground. Because otherwise 5 volts doesn't mean anything. So we'll take ground from this board and we'll plug it into ground over here. And actually, I'm not 100, oh no, oh God. Ground over here is what I meant. And I'm actually not sure if I have to power this from 5 volts as well. But since I have a 5 volt port, or 5 volts on my breadboard, I might as well. And it wouldn't surprise me if I had to, right? It's a, 5 volt logic and then, whatever you choose for your motor voltage. I suppose it's also possible at some point this evening that like I will, do something catastrophically wrong and like burn out the USB bus on my computer. And if that happens, then it's, it's been a good night and I'll see you next week. But fingers crossed, things will go all right. So now, I zoom you out, and as I add more and more stuff, we're just going to zoom further and further out, and you get to see more and more of the mess that is my workbench. So, okay, this is promising. Get this multimeter back over here into view. So now, if I measure at that point, yeah, so I'm at 3.3 volts. So, did I turn the power supply on, Chris? I did, but it's a very fair question. So let's turn this all the way clockwise again and see if we should get 0 volts. And then we'll dial it up from there. Yeah, nothing, 1 millivolt. So we said to get a maximum current of 1.5 amps, we want about 750 millivolts on this potentiometer. It's a little bit high. I'll dial that back down. And let's see here. I wouldn't hate being a little under 660, yeah, that seems fine. I think being a little bit underpowered to start with is probably safer than being a little bit overpowered. So that seems fine to me. Okay, well that's great. Now, Let's turn off power, we'll unplug the Arduino, and we'll get the stepper motor itself wired in, and get the Arduino wired up, and then test the darn thing. So, there's our stepper, and we're going to need some way for... I mean, I can hardly see if this bright silver shaft is spinning. I don't imagine it's terribly visible on camera. So in the grand tradition of nerds, we're going to add a little blue tape flag to it. It's 666 millivolts. Yeah, that's auspicious, I would call that. I think that's going to be... I think everything's coming up roses for us already this evening. So we will need 2 control lines going from the Arduino to the driver board. Let me see. They're going to need to be not this kind. We need a plug and a socket end. Let me pull a couple of those out of my big bin O DuPont connectors here. I know I've showed these off on stream before, but I'm so pleased. I have a bin of pin, I have a bin of pin socket, and I have a bin of socket to socket. And just like having those, I used to have them in like one giant bin container, and having them actually broken out is just, it's one of those little things that took, 20 minutes and is now like just a huge time saver every time I'm doing one of these things. So pin 2 on the Arduino will be my step control, and pin 3 will be my directional control. Yeah, let's write a little bit of code, and then we'll find out how it doesn't work. So let's see. So I wrote a little bit of code earlier just to make sure that I had my coding environment working, working out of VS Code here. So let us do a couple of things. Let's define step pin to be 2, and define dir pin to be 3. Let's save this real quick. We will call this, what do we call this? This is stepper test.ino. And we'll just do a real simple, like, by hand bit of code to make sure that this actually works. I should say it's been quite a while since we've written code on stream. So if the font size is weird, if things aren't showing up, if you want me to like pause and talk about things or blow through stuff, let me know. This is like I'm not in the rhythm of how to do this anymore. So if you're like, this is interesting, tell us more, or like, can you explain why you would do that? Happy to just carry along. Anyway. In our setup function here, we need to make sure that both of those pins are outputs. So we will do pin mode, step pin, output, pin mode, dir pin, output. No, Chris, I've gone to using VS Code. After the advice of somebody on a stream, I've been using the Arduino IDE for years because I just thought I'd been told that the plugins for VS Code for Arduino programming just weren't any good, and it turns out they're fine. And I work in VS Code, in Visual Studio Code, for basically everything else that I do, and writing in Python, and a little bit of hacks, and a little bit of C++. And so if I can write Arduino code in it, I'm just as happy. And I can upload directly from VS Code now, which is a huge plus. So let us... let's just do a really basic example, which should like step the motor back and forth. So we will say digital right, dir pin low, and I'm actually 100% sure which direction that'll be. So the direction pin attachment, or so I believe, and let me be clear, I could be getting all of this wrong, but from what I've researched and what I hope we'll learn together on stream tonight is by setting the directional pin on one of these drivers boards low, that will define us as spinning in one direction, and we'll pull it high to step the other direction. That's the theory. So we'll start by pulling low, and we'll say, let's do, these stepper motors in theory are 180 full steps to make a full revolution. So let's start it in full stepping mode, and we'll step it one full revolution one way and then the other. So we'll say for int I equals 0, I is less than 180, I plus plus. Digital right, step pin, high, delay, microseconds, which is a built-in, a part of the Arduino library, the wiring library, I don't know, 500 microseconds. I don't know what the minimum time is that we have to wait between steps. That might be something we have to pull from the datasheet in a little bit. Digital write, step pin low, delay, microseconds. In fact, now that I'm seeing we're going to see this a few times, let's pull this out into a variable. We'll say int wait between steps equals 500. And we'll just put that variable in here. Just so if we do need to, if I'm wrong about 500 microseconds being a good amount of time, we can change it in one place and not have to worry about it. Then we'll just go right into moving the other way. So we'll digital write dir pin high, and then we'll be a bad person. We'll copy and paste the code from above just to see if we can get this working. Yes. Pin high, pin low, and so on. 180 steps. Oh, thank you, Chris. No, you're totally right. It is 200 steps. Here, we'll say int steps per rotation is 200. You're right, I'm conflating two things. It's 200 steps and they're 1.8 degrees per step. Thank you. This is why I like having people who have done these things before around when I start faking it. So now in theory, I can plug in my Arduino here, and because you asked about the VS Code interface here, up in my palette here, because I've specified a board and serial port where I can do select serial port, and it pops up with, that's probably hard to see, I have two COM ports here. I have an FTDI chip and an Arduino identified, so I have a serial converter hooked up, an FTDI serial converter hooked up, but I want to use the Arduino. And I can say change board type. It's got a whole variety of boards, but I've selected Arduino Genuino Uno. And I can come up to my palette and just hit upload. And if everything has gone quite well, we should see some things happen. Oop, exited with code 1. What happened? Oh, you know what it is? Yeah, this is on me. I need to put this in its own folder. I put it in the same folder as the test I was doing earlier. And so it was finding it's finding the setup function twice and the loop function twice, which of course it was not very happy about. But now let's see if this will work. Verifying, oops. Exited with code 1, but why? Oh, is it because I have them both open in the editor? Be odd. Stepper test. I don't know. Let's try initializing packages, preparing boards, verifying, void loop in stepper test in test text. Now are we still? Yeah. So we are. Let me reload the stepper test from this other folder where I have saved it so that we're not seeing the same thing twice. And, oh, and you know what I should do is because I have this folder open in VS Code, let us just open the basic file. So I think it was trying to compile with everything that I had open in the editor, which is very nice of it, but it's not what I wanted to do. So we'll just close everything out and we'll open our stepper test file that we just wrote. And then we can try and upload. Oh, see, it popped up with an error. You might be still on there. Please select the board type first. So I'm going to go back in, change board type, and come down to Arduino/Genuino Uno. Probably going to make me select the serial port again. We'll say COM3, and let us try uploading that. Workspace doesn't have a folder added to it yet. All right, I'm happy to open a folder if that's what you need to upload things. Please select a board type first. Well, come on. It's probably because when I'm selecting the serial port and board type, it's saving them in the VS Code settings for this folder. And so if I don't have a folder open, it gets very grumpy. Let's try again. Preparing boards, verifying. Uploading. Hey, there's a good sign. All right, let's see how this goes. Now, I have not turned on my power supply yet, so nothing is happening. I mostly wanted to make sure we could actually upload. But power supply is on. doesn't look like it's doing anything, does it? Let me, here, let's make sure that this code is actually running. That will be a good thing to do. Let's define, oh, you know, we don't even have to define. We'll say pin mode, LED built-in output, and we'll make the output pin flash as we move through our loop. So digital write LED built-in high. We'll go through our loop. Digital write LED built-in low. We'll go through our loop. Okay, Arduino upload. Power supply is on and hooked up. So at least this way, like, we'll be able to tell if the Arduino is alive. Yeah, so, oh, wow. So that in theory, every time it goes on and off, it should be moving one full rotation, and that seems very fast to me. Dave makes a good point. Maybe it's an enable low system. Should probably read the documentation a little bit better, huh? Let's see. Enable, enable, enable. Yes. So you're absolutely right, Dave. It's active low. Oh, whoa! There it is. It must be a pull down on the board, or at least it's floating well enough that when I just unplugged it from high voltage, it just started going. Wow. Well, that works. Yeah, for sure. Yeah, I thank you, Dave. I did hardware. I was thinking I could move it over onto the board here, but it just moved over on the breadboard there. Wow, that's really something. So at some point, this stepping will start to fail, right? Like, I don't know what rate that is, but let's do a little experiment. So it's currently waiting half a millisecond between steps. What happens if we wait 250 milliseconds between steps? And re-upload. It doesn't go great. Although sometimes it is making the full revolution, but then it's often just stalling out. So that's clearly too fast. Here, let us slow down by quite a bit so we can see a little bit better what's going on. We'll wait 2 milliseconds between step. And re-upload. Oh, and you know what I should do is, while I'm thinking of it, in these loops, I should specify, instead of just looping to 200, I should be at steps per rotation. Now, it seems to me like we're maybe, are we still maybe missing steps? Like, it seems to me, just looking at this, I mean, maybe the tape is just bending in a weird way, but like, we're not making a full rotation each time. I wonder if we should be pausing in between. Yeah, right? Why am I losing steps, Chris? I wonder if we need to like pause just briefly in between each direction. Like, is it stuttering when it's trying to change direction immediately? I don't know. We'll put a little 100 millisecond delay in between each of the like direction reverses. You know what I'm also going to do is just, well, it'd be easier to do if this wasn't, hang on. Now that I know that I can enable and disable it, I'm just gonna move this tape up a little bit so it's definitely not rubbing on the body of the motor. That seems better. Yeah. Yeah. Oh, Chris, yeah, it needs to pause between directions. Yes, we're on the same wavelength. Well, that's better. Yes, Chris found that out from PLC and stepper motor experiments. I wonder what the minimum is we could tap that down to. Like, if we just did like a 20 millisecond delay would be 10 times as long as the individual step time. Let's see if that's good enough. No. No, we're still losing steps. So maybe 100 milliseconds was a safe choice, and it's a tenth of a second. So I think that'll be okay for us. Oops. It's funny, after years and years of using the Arduino IDE, I'm still defaulting to hitting Control U to upload the code, and of course it's not that anymore. It's in the palette. Well, that was easier than expected. So we'll play a little bit with micro-stepping these, and then there's a library, an Arduino library that I want to play with supposed to handle acceleration and things for you, which might be kind of fun. But this seems to have worked just fine. So let's disable this, and one of the nice things about these breakout boards is they have these built-in jumpers on them for configuring the step size of the stepper mode. Yeah, that's true, Chris. Like, I probably looking... I wonder how much the minimum pause between changing direction is a function of the chip, like the DRV8825, and how much... I would think it'd be as much about, like, the inductance of the windings of the motor as the chip itself, although the chip probably establishes a minimum. Let's see here. So I believe... Yeah, so then one of the nice things about these breakout boards is they have... We'll zoom in on them. Three little... Oops, I've disconnected my motor power. I'll let that just do its thing in the background there. Three little jumpers down here to allow you to set the step size directly on the board, right? So previously we were doing full steps, so we had 200 full steps in a revolution. Now we should be half stepping, so we're moving at half the speed, and we have 400 half steps per revolution. So if I go into our code, and I say we have 400 steps per revolution, and come back to our table here. Then once that uploads, we should be back to a full rotation each time, slower but smoother. And if we go to the very extreme ends of the spectrum, we actually get, so there are sort of two common commercial stepper drivers, it seems like they're out there, that have mostly evolved from things like 3D printers and homemade CNC machines and things like that. There's the A4998, I think is the other one, and this is the DRV8825. One of the reasons I went with this one, although they're pin compatible modules these days, but this one will go down to 30 seconds of a step, 132 of step. So if I increase our number of step sizes per revolution to 200 times 32, and we'll want to speed that back up some, or we'll be here all night. We'll re-upload, and now we should be back to doing full rotations, but taking whatever 200 times 32 is, 6,400 small steps per revolution. And now, I mean, it's just visually here, it's more buttery smooth than it was before, which is quite nice. Allows us quite a bit more precision. Now, I wonder, to your point, Chris, how fast could we get these to go? DRV8825. Let's do a quick look at the data sheet from our old friends at TI, who do know how to write a data sheet. Let's see here. Well, I can hide that for a sec. We can actually see this thing. Integrated motor driver, 2.5 amps of current. Let us see. So here's all our various pins, right? So this is all the pins on the actual IC itself, right? Not on this nice little breakout module that we have, which does handle some of these, like, tying all the ground connections together for us. Handling, operating, thermal, electrical level inputs, open drain outputs, decay input we don't have access to, H-bridge FETs, have a given on resistance, motor driver, protection circuitry, control, current control, timing requirements. Hey, here we go. So in theory, maximum step frequency, wow, is 200, it's probably a little hard to see there, is 250 kilohertz. Maximum pulse duration for step high is 2 microseconds, low is 2 microseconds. Holy crow. That's a lot faster than I would have thought. Well, let's crank this puppy up. Let's say we're gonna delay 10 microseconds in between each of these steps and see if it continues to play. That's very fast. Oh yeah. All right, so speed is not necessarily going to be an issue. I think that's going to be plenty fast for our purposes. Can we? I mean, so let's. I mean, just to push it, let's go down to 3 microseconds in between each, which nominally is within spec of the DRV, right? We'll upload that. No, not quite. So we may be running into. I mean, I wonder if we increased the current a little bit. No, not so much. All right, so we've established some kind of lower bound on. Chris says, if I never had problems with speed and steppers, it's always torque. Yeah, for sure. One of the reasons why I'm really curious about speed is like it's really going to define how fast our winch can move things up and down. I mean, compared, to be fair, to a scale chain motor, right? I guess speed is never really the defining thing, but still would be nice to move at more than a scale 60 inches per minute or something. But that's pretty perky. I think I'm quite happy with that. And that's at 30-second steps. That's 64,000 steps per revolution, or 64,000 micro steps per revolution, which is, I think, fine-grained enough control for us. Now, this is getting a little bit warm, but I think that's all right. Let me just real quick, I'm going to check in on the voltage on our calibration pin here and see if it'll tell us. Interestingly, that's gone. Oh, you know what I need to do is disable a driver. God, there was a little piece of lint just like floating around my workbench there, and I swore it was smoke. It gave me a fright. So I'm now at 780 millivolts. So I'm going to turn this voltage, this potentiometer back down just a hair. Back that power off just a little bit. And then we'll re-enable our driver. Oop, oop. And get it caught in my jumper here. So it looks like 5 microseconds is also a little bit too low. So let's go to like 8 microseconds. Hey. Did that not upload? Maybe it did. I guess it did. Oh, so 8 microseconds was sufficient between steps. So that's quite nice. Cool. Well, that worked out fairly well. So the next phase of things is I want to play with this acceleration library that someone's put together, which I think could be a useful thing for us to at least have, not that like a chain motor in the real world has any kind of measurable deceleration, right? You have that classic, the pickles moving the motor down and then clang, and it stops and it locks in place as the brakes kick in. But I think we could have a little bit of acceleration and deceleration on our winches. That might be a classy thing to have. So the library that I'm going to investigate is called Axle Stepper. And I'm just going to pull it down here. And I'm going to install it in my file system, Axle Stepper, and just like all other Arduino libraries, I believe I can just put it in the Arduino libraries folder in my documents here on the the old Windows machine. I wonder if I need to restart VS Code. Let's find out. Because it has IntelliSense here, if it is recognizing it, I should just be able to import it. Or include. Gosh, it's been... I am losing my mind. I mostly write Python these days. Yes, include, thank God. Hashtag include Excel stepper dot h. I'll tell you what, let us open up the Excel stepper library code and pull an example from it. See how it's, that's probably the fastest way for us to get a handle on what we actually are supposed to be doing with this acceleration library. Excel stepper, examples, constant speed, quick stop, proportional control. How about a bounce example? This seems fine. Make a single stepper bounce from one limit to the other. You know what we should do is just, let's just run this. Include stepper.h. Full 4-wire on pins. Interesting. So it's expecting us to possibly have a stepper that we have access to, like the full 4-wire interface as opposed to a single step pin through a driver. So that may or may not be the thing that we want, because we, of course, we want to use these nice motor drivers that we've used. This one references a motor shield. Let's see if that treats us all right. Motor latch, clock, enable, and data. I don't really like clocking data to this thing. That's not quite the use case that we're using. AF motor constant speed. Simplest fixed speed mode with no accelerations. AF stepper motor 1. Let's go to... So one of the nice things about working right in VS Code is... Let's see if I save this somewhere else so IntelliSense will work. Or if I copy this all to a new file and save it as an extension that VS Code understands. Let's call this AF motor demo, and we'll call the file AF motor demo.ino. And now, in theory, so like I want to know where, like what is this constructor doing up here? It's AF motor, stepper motor 1. I can right click and say go to definition. I won't find it. Damn, that's a real shame. Let's see. But I'm going to guess that this is the step pin and the number of steps per revolution. I'm sure there's documentation on it that I'm just not reading, but that's all right. Let's see here. So our step pin is going to be pin, what did I say, pin 2? I can steal it from our other example. Step pin is pin 2. Excel stepper, forward step, backward step, setup, begin serial port. I don't really want to do that. Set speed 5, run speed. Okay, I'll buy that. What happens if I try and upload you? Verifying. Uploading. That doesn't, I don't know that I believe that that's doing anything different. Oh, you know what it is, because I'm, okay, so this is a problem with VS Code, is I need to open the folder of the thing that I'm compiling, because it defaults to using the compilation settings that it established when I made that folder. So let's open our AF motor demo folder so that we have the proper folder open, and now we should be able to upload. Oh, select the board type first, sure. Arduino Uno. Select the serial port, it's the Arduino one, and upload. Now let's see what happens. Oop, it's terminated with an error. No afmotor.h, no such file or directory. So I wonder... Now, this is not a great global solution, but what I think I'm going to do just to get this working is to move that XL stepper library in its entirety into my project folder. I'm going to do that just off camera here. Let's see, what did we call this? AF stepper demo. Arduino, AF motor demo. We'll include AF stepper. All right, so let's try re-uploading this and see if it'll compile now. No such file or directory, AF motor. AF motor, here. I can show you what I'm, oops, not that tab though. I can show you file structure here. Interesting, AF motor doesn't exist in this class, unless it's in XL stepper.h. Huh. Well, that's unfortunate. Why don't we... Huh. This seems like it's not gonna do the thing that we want it to do. Huh. Well, you know, if we can't find a thing that makes it do what we want it to do, we can at least rip off the code from somebody who's already done some of the work. So let's see how this XL stepper library is doing its thing. We'll start by looking at the .h files, right? So in C++, right, you have these two different types of files. You have code files and you have header files. The header files pretty much are documentation and function and class declarations, and maybe some defines, and then you put your code, your methods, and your classes actually in your code file. So I am just going to start in, so this, like, the .h file, xlstepper.h, has like version history and documentation strings and change notes. And if we scroll down far enough, we should get some actual definitions. Yeah, here we go. Include standard lib, include wiring. Let's see. Support for stepper motors with acceleration. This defines a single 2-pin or 4-pin stepper motor, or stepper motor with F driver chip, whatever that means, with optional acceleration, deceleration, absolute positioning commands. That's exciting. Multiple steppers are supported, all moving with different speeds and accelerations. Operates by computing a time in microseconds. The step time is recomputed after each step, and after each speed and acceleration parameters are changed by the caller. The time of each step is recorded in microseconds. The run function steps the motor once if a new step is due. So we have to be basically constantly polling this library to make sure we catch those step times. Yes, the run function must be called frequently until the motor is in the desired position, after which the run will do nothing. Caveats. Thank you for including a section of caveats. This is an open loop controller. If the motor stalls or is over speed, XL stepper will not have a way to correctly identify where the motor is. Let's see. Driver. Using a stepper driver. That's really what I want. Constructor takes a... XL stepper takes an interface, 4-wire, pin 2, pin 3. Huh. All right, so maybe we can do what we want to do with this library. Caution, driver. What is this driver implementation? Driver means a stepper driver with step and direction pins. If an enable line is also, you would call set enable pin after construction. May also invert the pins using set pins inverted. Okay, so this actually does seem like it might do the thing that we want to do. So let's open up one of our examples again. Pull open our bounce example. We'll just copy and paste its code into the file we're working in for ease of use. And we're probably going to have to change our constructor here so that it takes not the 4-wire stepper motor function, but the driver parameter. Defaults to pin 2, which is step. which is, I think, matches what we had done in our other demo. Yes, Dave, when we're writing code in this channel, I sometimes feel like I'm just sort of saying pleasant words out loud. You know, this is my version of an ASMR channel. Let me look up what our pins are. Step is 2, direction is 3. Okay, so that does match what we'd already done. So we will say interface, pin 1 equals 2. Let's see. XL stepper, driver. Okay. Let's see if we can get this to upload. Oh, it's uploading. It's moving very slowly. Here, let's put it back into full step mode. Ooh, that's classy. So let's see when it gets to the end of its sort of rotation here. You can see it slows down and then comes back. Ooh, I like that. That's fun. Okay, so this was just code we ripped off of a demo. So let's see if we can actually understand what it's doing now. Set max speed, set acceleration, move to. What is this move to function? Let's go to the definition for that. Yeah, there we go. So this is one of the functions, like why to move away from the Arduino IDE and into an actual code editor, right? It's like I wanted to know what this move to function does. And not only can I just mouse over it and it gives me this tooltip and tells me, because the library writer has written some very nice doc strings, but I can also just go to the definition of it. So this is move to is doing some absolute positioning using a long integer. Which is quite nice. The move instruction is relative, move to is absolute. And let's see, set max speed. What are the units for this set max speed function? Let's go to definition. Here we go. Set max speed, float speed. And then the presumably minimum timing is inversely related to that speed parameter. So let's see. Let's set max speed to 200 and re-upload. Yeah, Chris, you can absolutely see the it's like sort of vibrates when it slows down. Here in person, you can actually tell it's doing that sort of all the time, just a little bit as it's single stepping. But it's certainly clear when it slows down and the steps become further apart. So interestingly, now we have sort of a high, whoa, missed a few steps there. That's interesting. So I guess max speed 200 is a little bit too high. We should probably try to understand a little bit better what that max speed parameter is. Let's see. Axle stepper, max speed. Set max speed takes a float. If it's less than 0, it gets inverted. If max speed is not equal to the speed we just input, right? So if something is actually changing, the new maximum speed equals the speed. This CMin parameter, minimum step size in microseconds based on max speed. Ah, that's nice. So we take the inverse of the speed and we recompute the next time that we would need to take a step. So, and this is what? This is 1 million megahertz divided by the speed. So our step time is 1 megahertz over the speed. So a speed input of 200 is too fast. I guess is what we're learning. Let's re-upload with a speed of 120. What is this? Let's see. Set acceleration. Clearly we're moving back and forth like much more slowly than we were just whipping this around with no acceleration. I don't want to necessarily sacrifice like raw speed just to make things smooth. But what I think is we can potentially, by decreasing the amount of time our motor is taking to accelerate and decelerate, we can sort of play with how fast we can get going in a certain amount of rotation. Divided by acceleration. So we'll just do a little experiment. What I was trying to figure out is like if we decrease the acceleration, so we went from 20 to 5, does that mean we're accelerating faster or slower? Oh, we'll re-upload and we'll see. You actually didn't get to see any of that. So acceleration of 5 is much slower acceleration. So what if we set our acceleration to 100? Cookie says, browsing the web for obscure hardware is a vibe. Cookie, what rabbit hole are you down tonight? So now, with that acceleration factor boosted some, I wonder if we can kick our speed back up. And, let's increase our travel distance some as well. Just so we have a little bit more runway to see this thing in action. Oh no, we're missing steps. Oh, that's awful. I wonder... Oof, yeah. Something... Oh, my power supply's become disconnected again, but... Oh, it's just not doing the thing. So we'll go back to step size 100 with our new fast acceleration and see if we can't get this to go at the speed that I think we should. Although maybe smooth acceleration at a slower speed is fine. Because to your point, Chris, like it doesn't necessarily need to go particularly fast. Let's see this thing decelerate quickly at the end of its travel. Pew! So that would probably be fine. So let's say this was moving at 120 RPM. Just to like make up number, like if this was our maximum move speed, right? So let's say this was moving at 120 RPM, and let's say we put a winding barrel on this that had a diameter of about 1 inch. So its circumference is about 3 inches. So a point on the circumference of that circle is moving 360 inches per minute or 30 feet per minute. So the height of the microstage is 2 feet, give or take. So that is moving that amount of distance in 1/15 of a minute, which is 4 seconds. Something seems to have gone wrong there. This is moving at... Oh, no. This is moving at 1 revolution every 2 seconds. It's moving at 30 RPM. So it would move, if for a 1-inch diameter barrel, the perimeter of it would move at 60 inches a minute. This is better. Yes, so 60 inches a minute, 5 feet per minute. So like 20-ish seconds, 25-ish seconds to go from top to bottom of the microstage. And that actually feels fine. It'd be nice to move a little faster. Although I certainly suppose we could always alternate control. Wow, that's really, really starting to heat up. We could experiment with moving back and forth between fast without acceleration and slow with acceleration modes. That might be kind of a fun thing to do. Oh, so Cookie, what are you up to? Cookie said, I want a square coupler to lock onto a steel rod so my spool doesn't turn independently. Found a hexagonal one. Ah, interesting. You're like a threaded rod coupler, basically. Yeah, if that's the species, and most of those are hexagonal. I don't know if I've ever seen a square one. Might have to fabricate one. That might be kind of fun. Well, I call this a success. Let's go back to our other demo here. So things that I like about this library. I'm not a huge fan of how it's handling step timing because clearly it's slowing us down. But the provision for acceleration is nice if we could have it. And maybe that's something we could pretty easily fake in our own code. I also like the idea of having both a relative and absolute positioning. Because that seems like a useful thing to have, especially as we're thinking about this as a DMX controllable device. Do we want to sort of follow the model of, gosh, why am I flaking on this? What is the company, Chris, you know them, and probably others do too, that makes like the DMX controlled, Wahlberg winches, is who I was trying to think of. I wonder what their control scheme is like. So Wahlberg, who's kind of the inspiration for some of this, right, makes these small little, like up to, I think 50 kilos is their largest one. Wow, the Winch 1. I don't think I've seen this before. It's like a 1 kilo winch system. And they're DMS controlled. They do have, I think, a passive e-stop loop, or at least some of them do. But it's like if you want to lift like, a microphone or a little chandelier, and it is a relatively inexpensive way to do so. What I was looking for is, what is their DMX schema, and is it good, and can we steal it? Mode functions. Positioning with auto top reset, positioning with manual top reset, manual run up, manual run down, only if specified. So DMX channels, position rough, DMX channel 2 position fine. Okay, so we have 16-bit positioning. Maximum speed, maximum travel top, maximum travel bottom, find top position moving up, and find position moving down. Okay. Place the rig in something high with minimum below. Set the DMX starters to 1 and the mode to 2. So in mode 2, we have positioning with manual top reset. Apply DMX from a lighting desk. Best if is a desk with manual faders. Make sure that your 7 channels are patched from DMX 1 to 7. Put them all at 0. Apply power to the winch. Pull channel 6 to 20%. Channel 6 is find top position moving up. Winch starts pulling the wire. Stop when the wire is in the top position. Now the winch has found its top position and is ready to drive with position control. Pull channel 1 to 95%, pull channel 3 to 20%. It moves down to 20% with 20% speed. Okay. Wow, so you really you calibrate it once using DMX and then it remembers what those absolute positions are. That's not an awful way for a thing to be addressed, assuming it's DMX. Chris says, I keep thinking the DMX spec is not meant for winches or automation. So I don't... Well, I'll tell you what, I have the DMX spec just here. And Dave, I don't know if you're were saying you wanted more story time or less, but given the opportunity for a story, I'm not going to say no. So let's do a little investigation, because I think Chris, I think certainly true that it's not really what it is meant for. Certainly, it is not an error-checked protocol in any sense. But that doesn't stop people from doing silly things with it. Appropriate uses of the standard, section 1.3 of ESTA 111. Equipment designers and general users of this standard will recognize that this standard is intended to only fulfill a limited range of uses, cannot process codes in a timely manner. Section 1.4 and 1.5 does say DMX 512 is designed to carry repetitive control data from a single controller to one or more receivers. This protocol is intended to be used to control dimmers, other lighting devices, and related non-hazardous effects equipment. So, I feel like lifting something overhead is maybe a gray area there. Like, is lifting a 1 pound thing overhead non-hazardous? I mean, arguably yes, for sure, but arguably it's a little questionable. Since the standard does not mandate error checking, DMX 512 is not an appropriate control protocol for hazardous applications. Certainly think we would find in there. He says an OSHA violation for loads need a dead man switch in line. Oh, that's interesting. Yeah, does it more than just entertainment standards? Are we violating OSHA standards by doing something like this? Pre, do you happen to, off the top of your head, like which section of OSHA code that might fall under? That might be an interesting thing to take a look at. So the rest of this is technical specification. I don't think we're going to find other applicability data here other than ESTA saying that like DMX is not fair enough, Cookie. Yeah, no need to be an expert on OSHA for sure. The goodness knows. I mean, who is? Yeah, I think this is all going to be normative stuff. Interesting, fascinating ways to transmit UTF-8 data over DMX, right? A standardized start packet for testing your network capabilities. System information packet that encodes like state of your system. Yeah, all a fascinating standard to read, but not necessarily going to tell us the thing. Only no, because Cookie says only had chain hoist on DMX relays with an e-stop, but it's supposed to be a dead man switch. I mean, I would certainly agree. Like there needs to be a dead man in somewhere whenever there's a motor moving something, I guess, period, or really, towards somebody or around anybody. Where was our user manual here? So yeah, so just looking at these, like, so I saw these in person at USITT one year, and I feel like they had an e-stop, a passive e-stop loop that was four-wire XLR, I think. Though I'm not seeing them on here. DMX in and through, fuses and power. Power inlet, power consumption. Yeah, I could have sworn they had a passive. Maybe it's on the larger models? There's a winch 25. So the idea was, right, you'd at least have like a passive loop of 4-pin wire. Oh, here we go. Yes, so I don't know if you can see this terribly well. Let's see if we can zoom in a little bit here. Probably not. But you have DMX in and through, power in, and then e-stop, which is like a normally closed control signal. And so if you break it with an e-stop anywhere in like a series of e-stop lines, the winch faults, is the idea. So it's interesting that it has... This is the winch 25, which is sort of the smallest of their like larger winch line. I don't see it on any of the smaller designs. Interesting. Power consumption, snap put, fleet angle, mounting clamp. Yeah, it's like they don't mention it anywhere, so I'm assuming those don't have any. Anyway, we're way off the given topic tonight, but I'm happy to like steal good ideas from actual manufacturers whenever we can. So yeah, so there's that. So I think the next step is going to be thinking about how we integrate the stepper motor with the winch mechanism that we were looking at earlier. So I think for the sake of that, so we sort of learned what we needed to, that like the driver board works, and ultimately like I don't necessarily plan to use like a Amazon bought driver board to control these things, although for experimentation purposes they're very handy. What exactly the control PCB looks like in the end, I'm not entirely sure, although I do think it probably has like an off-the-shelf driver module that sockets in like this, so just to make things a little bit easier. Chris says the Warbirds are fairly quiet from remembering at USITT. Yeah, I don't think they were horribly loud, but I think what I'm going to do is just, actually probably just unplug this. I'm just going to remove the stepper from the electronics for a second, just put it next to the winch mechanism and use that as a way to start thinking about the the mechanics of this. So one of the reasons I size this frame to be the size that it is that with the NEMA 17 stepper motor centered on the shaft, it is just a little bit shorter there than the frame itself. See, so slightly off center there, so this raises up by like 1 millimeter or 2. So the mounting hardware for this stepper motor can be relatively slim. And of course, this is all mounted. I put all my truss away. The tiny bit of cleaning I have done this week in this shop, which is a disaster, took away like the 2 things that I needed. So if this is looked at in profile, right, we'd have our winch mechanism hooked up here. We'd have our stepper motor hanging on some kind of bracket here. We'd have a coupler. Now, of course, this can't be coupled directly to the shaft. This would have to be coupled via one of our, the equivalent of this handle wheel, right? That's got to be the interface between these two. And this is sort of the next point of like 3D design that I think is going to be necessary. So I had printed another one of these handle wheels for the demo, but like I say, the shop is a mess. One of the key functionalities of this handle wheel that's necessary for the operation of this winch mechanism is that as the motor drives this wheel to pull the load in, right? If this is hanging underneath the truss to pull the pipe or whatever upward, this is going to have to move inward toward the winch body. You're going to have to tighten onto that thread just a little bit. And as this loosens, it's going to have to move outward radially just a little bit. So I think the easiest thing to do is basically going to be to extend the cap, if you will, of this handle wheel with a D-shaped hole that matches the D shape of this shaft. You can see it's squared off on one side, but we're not actually going to apply like a set screw or something to keep it captive. We're just going to make this like, an 8 or 10 millimeter, hollow hole so that as that wheel needs to travel inward or outward from the winch mechanism, it has the ability to do so, right? So we're going to basically extend this hole a little bit, make it a fairly tight fit to that D shaft, but then we'll probably lubricate it and sand it so that like as it needs to move those couple of threads in and out to make this winch work, it has the play to do that. So let's, I'll tell you what, let's do that in Fusion just now and then see, I don't know, where else the mice takes us. Also going to have to butte fusions, which is going to take a second. So a good time for a hydration break and question. Crit is the motor moves faster than the load tightens up. You just unscrew the entire thing. Yeah, that is would be unfortunate for sure. Think about exactly what this motor mount looks like that keeps this NEMA motor really securely affixed to this truss. So I had been thinking about repurposing, and I probably actually still could. I mean, we made great use of our little S-shaped snap hooks for the Demilight project and for the Kabuki drop. You remember these little snap pins? And I'm thinking that there's maybe a way. Positioning is the problem because they do have to stick into the body of the thing. It would be, for stability, it'd be really nice to keep the winch, I think, pressed up against the bottom of the truss, which is not how anything else is mounted on the system. There's just going to be a fair amount of force on this thing. Since these S-hooks don't actually affirmatively lock anything in place. Then now I'm just sort of fiddling around while Fusion boots and thinks about what it's done. Like this snap pin could maybe, you can sort of see these posts are solid. Like we could mount the 2 snap hooks inside of there. And maybe a snap hook just there if we thickened up the bottom frame, and we could tie it into one of these cross members here. So it would sort of sit like that. And do a similar thing for the motor. That's kind of interesting. I like the idea. These snap hooks have proved so versatile and they've been so easy as I've been moving things around to prototype. I do like the idea of continuing to use them. So maybe that's the thing. Maybe we'll etch some snap hook holes into this frame. and then repurpose some kind of mount for this guy. So let me pull up, now that Fusion is decided to do its thing. Let me just pull up my editable documents and open up my new truss winch. So this is, I guess I don't know how clear any of the explanation of how this mechanism actually worked was from trying to zoom in on the table, but this is the gist of it in Fusion, right? It's a mount that's just meant to hold the bearing and the barrel. There's our barrel shaft, and of course we have our actual bearing, our 608 bearing there, which I'll turn off for the sake of visibility. And then we have our ratchet wheel, right, that just slips around that arbor there. We have our handle wheel, which will apply friction on top of it. And then we have our pawl assembly, which is two symmetrical pieces that slide into each other and go into those two slots. So, and some changes to be made there, obviously, but what we came in here to do was to get into this handle wheel and make a D-shaped hole in it. So let's see how much. Let's go into our handle wheel assembly. Go to the point after we put the threads into it. That's critical. And let's see how much room I left myself at the base of this handle wheel. 5 millimeters? I don't know that that's necessarily going to cut it. Grab my calipers here. So the D-shaped portion of this shaft, because that shaft is not notched, is not D-shaped all the way to the housing, but it looks like I'll use the depthing tool in the back of my calipers here. Looks like that is 17.62 millimeters. So if we were to make a 15 millimeter section there of D-shaped hole, that would be enough for almost all of the thread. So let's figure out where that extrusion is. It's right here. So let's give ourselves 20 millimeters to work with. And then we'll extrude a D-shaped hole back into it. So the diameter of my shaft here is... I'm sure these are all standard dimensions as well. It's 5 millimeters, right? And so we'll make this 5 point... let's make this 5.2. How much slop do we want to have in this is part of my question. 5.15 maybe, just based on my printer. Let's bring this across, and let's make sure that line is coincident with the circle, and it's horizontal, and the diameter across this D-shaped section, my calipers here. Yeah, exactly, Chris. So that's what I was using the depthing section for, was just to make sure that we use the little depthing stud there to see that we have, well, now I have unzeroed it. Oh, I'm back in inches as well. We'll just use the little depthing stud to see that we have about 17.5 millimeters. So I'm going to make a 15 millimeter hole, and we'll just know we're never going to bottom out to the bottom of that D. And the diameter across our D-shaped section here is 4.45 millimeters. So that would be the dimension from, say, the top of the circle here. Here was 4.45, so with some clearance, let's say it's 4.5. Probably want to keep that fairly tight, maybe 4.55. And we'll extrude that shape in by 15 millimeters and cut. Okay, so there's our D-shaped shaft for our attachment there. So let's see that in context. And you know what's occurring to me now is, so I've been thinking about how do we, as we noticed earlier, there were some issues with, now this whole assembly is going to be a little bit supported by the stepper motor shaft here, but other than that, it's really only supported by the bearing way over at the other end of this assembly. So we really should find a way to put some some lateral support here so the pawls, the springs in those pawls are not just moving this thing all over the place. And I think the obvious place to do it is in this shaft section, which is where we're going to be applying more torque anyway. And we could put another bearing here, potentially. That might be kind of a nice thing to do. In fact, let's do that. So let us modify our. Let's start by modifying our handle wheel here, and we'll put a spot for another bearing in it. We'll go 10 millimeters. Go 8 millimeters down. Let's see. So let's center it. No, let's how do we want to orient this? Let's put this 7 millimeters down this way. And what was the dimensions of our hole over here? So this is our hole for our bearing in the frame on the other side, which I've dialed in fairly well, is a 22.2 millimeter diameter hole, and the interior is 8.15 millimeters for the shaft. So we will make a new sketch on this plane, intersect our existing barrel, intersect our whole body of our existing barrel. And then I'm just going to turn some things off so we can see what we're doing. So now concentric with that, we'll do a 22.2 millimeter. We'll do an 8.15 millimeter section. Finish sketch, and then let me see, how deep do we make this frame to line up with that other bearing? 1 and 2. 7 millimeters seems fine. So we'll turn our handle wheel back on. And oh, I put that sketch in the wrong part. Dang. All right, I'm gonna be persnickety. I was really lazy about keeping my components clean in the original design of this thing, and I feel like since I sort of started over from scratch, I'm going to be really particular about keeping all of the operations in the correct component. So we'll undo a little bit of work there, just to keep things clean. So we'll say this was 8.15 millimeters is the diameter for the inner part of our shaft. Finish sketch, and we'll extrude cut that portion for, let's say, 7.3 minus 7.3 millimeters. Which seems, except how are we going to get this into the bearing? Oh, bummer. Yeah, okay, so this would have to... this would have to look something more like that. Which is fine, I guess. There's not a lot of room here for that, not a lot of space for that, that shaft to act on. Yeah, we got some sweet jams going on tonight. Right, but so the idea is, like, you know, let's put this back in context. Let's turn the frame back on. Right, we put another bearing out here and help support things. Yeah, Chris, not only getting the bearing on, but in more of a sense, like if that bearing is part of the frame, getting this handle wheel in place becomes an issue. Let's back this up. Let's think if this is really the most logical place to put a bearing. Put the bearing right at the end over the shaft. So put it like, could put it like out here, so to speak. Yeah. Just thinking is like, is there like, could it? I don't really. It doesn't. Okay, so let's think this through. Let me turn the frame off here. It can't really go. Can't go in this section because this is all about the pawl. It can't go in really in this section because this is the point where the force from the handle wheel is being translated to the friction washer that exists between here. So it's really got to be out in this section. So yeah, so maybe right out at the end here is best. So let's take this to 8.15. And we'll extrude it 7 millimeters. So if the bearing is going to be there, you know what I think, Chris. So I'm trying to figure out how would you actually assemble this if the frame came out to incorporate like this other bearing, but I think it's a separate frame unit that includes both this separate bearing and the stepper motor. Do you need it? Won't the motor keep things in places, Chris? I mean, yes. That's I don't know. Because yeah, so the motor. I wonder. Well, let's do a little side mission. Let's see if we can find a model of a NEMA 17 stepper motor that we can drop in. Maybe something specifically like this one. I don't know if McMaster has stepper motors. It sort of seems outside of their competency. Oh, I spoke too soon. NEMA 17, sorted by overall length. Oh, wow. All right, I'll measure the overall length of my stepper motor, sure. In inches, it looks like they're measuring them in. This is 1 7/8. That's actually smaller than any of the options here. But that's okay. We can bring it in and then modify it if we have to. Width and height are standard. Let's see if I guess these have 3D models. Yeah, Cookie, right? Like I wouldn't have guessed that in a minute. Now these are always larger than the ones that I have. Chris says they're crazy expensive. How expensive are they? Well, these ones are $63 a piece, but like we're not gonna buy these. We're just gonna steal the model, right? Let's see, 3D step. Yes, we'll pull that in. I have definitely stolen models for things like whatchamacallums, aluminum extrusion, like 2020 from McMaster before. I don't buy 2020 from there because very expensive, but I guess I should verify. I mean, we're clearly not going to be able to do any direct modeling off of this, right? Because it's not the same size as our thing. Maybe we'll go to GrabCAD and see what we can do. But it's at least just like to give us a little bit of context. Here, I'll tell you what. Let's do a point-to-point move with the end of this shaft and the bottom of the hole in this guy. And then we will just move this back like a millimeter or two. So we could have a, I guess I should verify, roughly speaking, that this is like similar dimensions. Yeah, 1 3/4 inch. So this 3D model from McMaster is a little bit larger radially than mine is, and it is a little bit deeper than mine. But just for illustrative purposes, right? So we have the same thing to talk about. So we're thinking, Chris, we could put that bearing just here if we need it, or does the motor do a good enough job of just supporting this? I guess I worry that as you know, we have these two pawls that are applying torque to this barrel already, like putting some lateral force. I worry that this motor is not going to be enough on its own, since it's also going to be applying a fair amount of force to prevent this from going all sort of cattywampus as it tries to apply some force to the mechanism. That's my worry. I guess I won't really know until we try it. But my impulse is to model the bearing in, try it, and then just with the same mount and everything, just knock the bearing out and put this shaft back together and see how it operates, you know? And if that works, then we'll just slim the frame down so it doesn't need to hold a bearing anymore. I think is the way to go. So speaking of, let's pull another bearing in here. We will find 608 bearing. They are all, there's lots of, you can find all of the different ones on here, but I'm gonna just pick the one that's actually what I have. We'll download a step file of it. We'll do a nice point-to-point move of that bearing surface and that surface, and we'll capture. So that's going to be our new bearing, although I guess we're going to move this just a little bit offset here. Oops. Leave like a millimeter of clearance just there. Actually, probably what I want to do is leave that there and make this cut a little bit deeper, huh? Oops. Oh no. Fusion, no, why? Fusion, I believe, is crashing, is the technical term. I can no longer select things in the timeline. Well, it at least let me save, so that's very exciting. That's if Fusion is going to glitch out on me, that is its most common failure mode. I don't know what y'all experience, but well, all of a sudden, like, I can't edit previous operations and the timeline becomes super janky. Like, maybe I can move the history marker forward or back, or maybe I can only move it backward but can't move back forward again. At that point, the only solution that I found really is to like exit and reload. So here we are. But thankfully, at least on my PC, it now loads relatively quickly. Oop, is that? Yeah, there we go. So this is what we were working on here. So now let's go back to that cut it wouldn't let me edit earlier. Yes, and now I can, which is great. Now our bearing has a little bit of clearance there. So yeah, so I think what I'm going to do, and I won't make you sit through all of it, is basically design and obviously would need to have a more accurate modeling of what my actual stepper motors that I'm going to use are, and think a little bit about how they're going to be mounted, is make a second frame like to this one that has a hole for this bearing and a mount for this stepper, and think about how they're going to both mount up to a piece of truss that sits above them. And then it will be super easy to experiment, like I say, with we'll try it with and without the bearing, and if the bearing's unnecessary, fantastic, and we'll just slim this mount down and take the bearing out of it. So I'd say I don't know. And we'll need to come up with a new coupler that couples this winch shaft. What will be a shaft? What I think is going to be. I haven't decided if this is actually going to be the thing, but these shafts are going to need some strength to them. So I actually purchased some 3/16 diameter galvanized steel rod just from a local hardware store that I think is going to be our winch shaft. I chose 3/16 because the same OD as that brass rod we happen to use for the kabuki mechanism, and it felt about right, but it's also got significantly more, we could put some torque on this and have some confidence in it, which I like. So that I think is going to be our winch shaft that actually we mount some what do we call those? We mount some lifting wheels to wind up our spools of line onto. And then maybe another piece of this is also our batten down below that things hang off of. TBD, exactly what that looks like. Maybe one of these is our batten, and we come up with a new design of the snap hook that has this is sized for a slightly smaller cord. So maybe we come up with a slightly tighter design for this that snaps onto a 3/16 rod. So then we'll have a snap hook that snaps to, what is it, Cookies? It's 6mm cord. And then some that snaps to a 3/16 cord. Just to really when somebody discovers this product, they're like, what country did, how. That would give me some great delight. Oh, you has similar rod stock in your Amazon shopping cart. Yes, amazing. Yeah, it's just, it feels about right, which is what really matters here. Well, neat. I think that's going to be exciting. Yeah, I think that's where we're going to wrap it up for tonight, y'all. I don't think, until I understand a little bit more about what's going on in that acceleration stepper library, I'm ready to take the plunge into trying to get stepper motors and DMX to play nicely together, which they might just do. They'll play okay. Will they play great? Unclear. And to be totally honest, I have a project I'm consulting on in the next couple weeks that's going to require a fairly in-depth analysis of DMX timing versus the internal state of the Arduino's timers, that I will talk more on when it's complete and done. But once I have done that, I think I will have a lot more tools to digest what's going on with that acceleration library. So it sort of makes sense for me actually now to just to put that off a little bit, and we'll come back to that at a future time. But yeah, fun experiments. I'm glad that's, short of forgetting that the enable pin was active low, thank you, Dave, that this just worked and spun and has a fair amount of torque. So we'll have some more fun experiments to play with there, and some more mounts to calibrate as we think about mounting this to an actual system. But yeah, I think that'll be it for tonight. As always, thank you for spending a Sunday night here with me, being nerds. I appreciate all the good advice for those who know these things better than I do. Hope you're staying safe out there, washing your hands, hydrating, getting your shots when you can. By the next time you see me here live, I will have all of the antibodies I could ever want in me, so I'm very happy about that. Yeah, I hope you're all doing well out there. It's a real privilege to have these hours to spare on these Sunday nights to say hi to y'all. So be well, make cool things, and I will see you next week. Thanks, y'all.